So in this video here, we're going to just quickly go over our pitch and conceptual Doppler problems. And then tomorrow we'll spend more time going through the Doppler formula. This will be pretty quick. And then after going over this assignment here, I have a short homework assignment for you in Google Classroom. That's just more of these questions. So that way at home I can get an idea of how everybody is doing on these topics here, just to get a little bit of feedback for myself. Okay, so in our first problem, so here we have object, or in this case a person A, person B, and we have something that is emitting sound that is moving. And so you're asked to draw an arrow to indicate the direction that the object has to be moving, and if it's not moving, explain why it's not. So whenever something emits sound, and it's not moving, it's going to emit sound evenly in all directions. If something starts to move, it's going to compress those sound waves in the direction that it's moving. And so if those sound waves get compressed, they get closer together, that increases then the frequency, since you have more waves occurring in a shorter amount of time, shorter amount of space, and so that's going to sound like a higher pitch. On the opposite end of things, if the waves are elongated or stretched out, that's going to lower the pitch. So the frequency decreases, it's not as high. So in this particular problem, the dot is moving towards the right, towards person B. We know this because the frequency in this section is higher. There's more wavelengths occurring in a shorter amount of space. So person B would hear a higher pitch. Person A would hear a lower pitch because the waves are stretched out and the waves are also less frequent. This is our stationary example. So in this particular example, here I have A and B. My dot is in the center, and notice the waves are evenly spread out in all directions. So if they're even in all directions, then person A and B would hear the same pitch. The wavelength the same, so that means the frequency is the same. So both A and B would perceive the same frequency sound since the object is not moving. So it's emitting the sound evenly in all directions. With our next one, we had to determine the order of the waves from highest pitch to lowest pitch. So pitch goes with frequency. So I want to find the wave picture that has the highest frequency, so the most waves occurring within the second's worth of time. And then kind of work my way backwards to the longest, most stretched out, lowest frequency wave. So B, I have a lot of waves occurring in a second's worth of time. So highest frequency, highest pitch. And then our next one here, this wave has a higher frequency than this one. So this would be number 2. This one is higher than this one. So this one would be 3. And then here I pretty much just have one single wavelength in a second's worth of time. So this would be my lowest frequency wave, or in turn my lowest pitched wave. Loudness is related to amplitude. So not necessarily how many wavelengths I have, but how high that displacement is from rest. So of these 3, you had to organize between which wave would be the loudest to which would be the quietest. And so, again, we're going by amplitude. So this has the highest displacement. So this would be the loudest wave. So this would be number 1. And then I know the copier here for my key has an extra line here. But on your paper here, so we have this as our mean position. So this displacement is a little bit taller than from here to here. So this would be our second loudest wave, so our second highest amplitude. And then our shortest amplitude here would be number 3, so this would be our quieter wave. More Doppler problems on the back, and so we're going to stick with the same idea of if something is stationary, then it doesn't matter who person A, person B is. where their position is all around. If the wavelengths are even, that means the frequency is even, and so they're going to all hear the same pitch, no matter where their position is. So this middle one here has an object that is not moving, it's stationary, so same frequency, same wavelength, same pitch. And this one here, A would hear a higher pitch than B because my dot is moving towards A, so compressing those waves in a smaller area of space, increasing the frequency of those waves. So higher frequency, higher pitch. B would hear a lower pitch because the wavelengths are stretched out and farther spaced apart. And in this model here, so in this case, A would hear the lower pitch, B would hear the higher pitch because we have a greater area of compression towards B. A is more stretched out, longer wavelength, lower frequency, lower pitch. Here you had to read about musical instruments, resonance, and got to learn a little bit too on why you can quote unquote hear the ocean when you're listening to a large seashell. So these next three questions, we're just kind of summarizing the big ideas from the reading, but if you want to make sure your summary was right on track, as long as we have something similar, it doesn't need to be word for word what I have here, similar, and then we can conclude, assume that we are doing A-okay on this topic too. So resonance is when one object is vibrating at the same natural frequency as a second, and that forces the second object into vibrational motion. So all substances have like a set frequency, a natural frequency in which they are going to vibrate. If a disturbance can make them vibrate and shake and emit sound. So if I have one thing that's vibrating at a frequency that can set another object, something totally different, also into vibration at the same frequency, then those two objects are said to be in resonance, or resonance is said to be happening in the system. So with musical instruments, instruments in general are just set into vibration of some way, shape, or form when the instrument is disturbed. So a smack, a pluck. So instruments can be forced to vibrate. Specifically, the reading calls it a harmonic. If the disturbance on the instrument is set at that harmonic frequency. And then seashell up against your ear. So why do we hear the ocean? So the reading talked about how there's lots of sounds in the room, and sometimes they can be very quiet, inaudible for you to hear just on your own with your ears. However, if one of those frequency sound waves in the room is the same frequency at the seashell's natural frequency of vibration, then that other sound can set the seashell into resonance. So it can cause that seashell to vibrate on its own from the other sound. And so when you put your ear up against to the shell, you can hear, quote unquote, the wave, when in reality it's simply just that seashell vibrating due to some background noise being at the natural frequency of the seashell. So I do have a video that is posted if you think you need further reinforcements on this topic, the conceptual stuff with Doppler, or the understanding the difference between loudness as well as pitch. But if you're feeling pretty good, there are a few questions that is posted in Google Classroom as a Google form. So answer those questions, make sure you submit it when you're done, and that'll give me a good idea of how well notes went today. Any questions, feel free to email me.